because you can't have too many recordings. Right, so processing has a coordinate system in it, right? So how many of you downloaded and got processing on your machines? Excellent, that's fabulous. One of the first things you might notice when you start working in processing is it flips its coordinate system. So when you started to draw a line and you did, oh, I want to draw a line from the bottom to the top, I'll draw it from 1010 up to 9090. But unfortunately, that's not how processing sees the world. Processing, like many computer graphics programs, sees the top corner here, right, at 0, 0, as the origin, right? That's the start of the array that represents the image. So the first row runs across to 99 in X, and the second row is the line below that. So that means that kind of the Y is inverted. So you have to kind of think in your head that Y, positive Y, now points down the page rather than up the page. So that's something you'll have to flip in your head when you're using computer graphics. Some computer graphics programs and some game programming systems allow you to change that coordinate system, say, well, actually, I want Y to be up. However, this uses the older format of saying, well, no, 0, 0 is there, Y is down the screen, and X is across the screen. So 0, 0 is the top left. The default window size is tiny at 100 by 100 pixels. Because when you had a 300 by 400 pixel monitor, 100 by 100 was like, a third, right? It came across with a 30 monitor. But any of you using anything modern will find that that's a tiny, tiny wee square somewhere in the corner. So often we'll be changing the size of these systems. Oh, it went up. I didn't realize that it had that animation. So if we do line 1010 to 99, what we actually find is that we draw down by going up. Right? So that's the first kind of interesting thing about processing. We're using the Java version. It also hides away all of the boilerplate stuff that you need to do to set up classes, to set up a window, to get a window handle, to attach your code to the window and do it. It hides all of that and they say, yeah, if you want to start sketching stuff, just tell me what to do and I'll just immediately do it. Right? It's one of the differences between like using Java Swing or using C++ and graphical languages is that there's a lot of other stuff you do. Processing is designed around just getting the graphics out there as quickly as possible in as relatively simple way as possible. So that's a simple line 99. We then have the ability to draw more lines, and so an arrow is just a line with 2 more lines. Right? So again, just simple instructions, and here we're in direct mode. Right? So I just tell it something, and it just immediately does it. If we go along, I can then go, okay, well actually I need to clean those up because that's very badly blurred. This, as we see, is line 10 to 90, 99. So I drew the line, I drew an arrow, I drew the line, I drew another arrow here. But here I've changed the numbers just so it goes down the page by having high Y rather than across the page. So all of that makes sense? We're all nodding? Yep, okay. We'll move through this relatively quickly because I've got quite a lot of stuff to cover. So one way of doing repeated lines, certainly you've done this, is just to manually write a whole bunch of lines, and then you have to manually work out where all of these positions are. Right? Of course, you've done 102 or 112, so you know we should really have a for loop, which has a variable that you then draw the lines with a loop. Right? And of course, we can do that sort of thing. We can also change the background. Here, you see background 0. So what's background 0 doing? What does background 0 do?
Inverting the colour.
Close. It's not quite inverting the colour, but that's a good idea. Yep.
Black from 0 colour.
It sets it to 0, 0, 0. It sets it to black in each of the categories. So yes, it sets it to black. What background does is it actually draws the entire screen. Every pixel gets changed to black when you call background black. It just draws over everything with a black area. If you did a number between 0 and 255, you'll get a grey value because it's an equal amount of red, green, and blue. Stroke. Stroke 255. Any idea what stroke does? Yep.
Just setting it to white.
Setting it to white. Yes, 255 is white, you're right. And what is stroke?
Colored.
All lines.
The line. It's the colour of the lines, right? So we have two things in processing. You have strokes and fill. Stroke is the line you draw, and fill is what's inside that. Right? So here we set background to 0, stroke to white, stroke weight to 5, makes it nice and fat because that's 5 pixels, and we use weight there to refer to the width and the sort of how heavy it is, right? Because it's a thick line. So again, those 5 lines now background, white coloured, that's thicker. That 5 actually refers to the number of pixels, right? This is very much a direct referencing system where each position I'm referring to here is a pixel position. And so if we zoom into those pixel positions, you can see that for the stroke of a box, this is 1 pixel wide. Right, so very simple, direct pixel referencing, one pixel wide, and then each of these grey squares is a grey pixel. For text, like writing the text 0, you find that there might be one that might be black, but the rest of them are usually a grey level to give us the illusion that there's a smooth path that is going through different small pixels. Okay, so that's why you get those blurry, not quite either black or white, but a grey scale. Now you would never, well, okay, we used to, in some distant past, actually have to program that sort of stuff and decide how much things were. Our graphics cards and our graphics systems will do all of that for us now. We will discuss how you do that so you understand the algorithms behind creating those appropriately smooth curves through a very pixelated world. So, if we have a look, you can, as I said, directly access those individual pixels. Right? So here we have 4 dots, and it's these dots here are being drawn. So you've got those dots in the top left, and you've got, you know, bottom right in the bottom corner here, a couple of pixels there, and the 4 sentinel pixels. Okay, so those are just directly accessing every individual pixel in that 100 by 100 area. That'd be a really slow way to do computer graphics. It's pixel by pixel. It's a bit like doing ASCII art, slow and challenging. So if we have a look, we've got whole images. Okay, so we've looked at the processing does things on pixels. What do we mean by a digital image and what do we mean by pixels? Well, an image, now we're building up an image, is in this case, technically, we describe it as some sort of image. So if you include photographs, normal, actually I don't know, how many of you actually hold like actual photographs versus prints from a phone? Do any of you actually have old photographs? You're probably old photographs. Yeah, yeah. So they're an image, right? So they've been imaged, and how they were captured was not digital. They used a chemical reaction where light would hit the photographic plate and generate a change in the chemistry to make it, to change the response to light, which would then give you a negative, and then you would turn that through illumination into the colour print. Right? So we're using analog colour response by chemical reaction. So we didn't have really a resolution on a photograph because every chemical, every single molecule in that photographic paper would be responding. Right? So it was, you know, what might be considered thousands of chemical molecules per image. So when we refer to image, I don't just mean the digital images you take with your phone or the images you create with processing. We actually refer to all images. And technically, mathematically, we describe that as a two-dimensional area, right? It's a two-dimensional function where it defines a colour at every point, not at every quantized point, right? So you don't have pixel 2, 5, you don't have pixel 2, you don't have pixel 7. You just have some real valued number has some real valued colour at it, right? So it's completely analog and completely smooth. That's not a digital image. What we mean by a digital image is that we then sample and quantize the image. So what you're producing and processing is a digital image because you're producing something that's quantized between 0 and 255 in each of the colours, and something that is sampled at specific places in what appears to be a smooth, large image. So here we're sampling in a rectangular grid. Some of your televisions, actually, the pixels of TVs can be odd, different shapes. You can have pentagonal, sort of the pixels, the pentagonal OLED screens. You can have different low-level shapes and more greens or more blues depending on the monitor you're using. But how we do it on your hardware is in a rectangular grid rather than a hexagonal grid or any others. And it's quantized because it's set at specific quanta, specific countable numbers. Right? So that's 0, in this case, we're using what's called full colour at 0 to 255 per colour channel. Right? So it's 1 byte per colour channel. You can have systems that give you more values per colour channel, but what we've found is that most of you can't tell the difference in colours when we only change one value in one part of the blue spectrum. So I give you say, a red, green, blue value, and I change the blue from 255 to 254 and ask you to spot that. It's kind of, ooh, my eyes really, I just can't quite differentiate it. If I draw certain patterns, you can, but you have to kind of really work hard. And so this is set at the almost imperceptible to humans difference. Right? So generally we don't need to go higher than that. So quantized, a set amount of intensity, and sampled, how often we sample it. If you're interested in quantum mechanics, it appears that the universe is also quantized, just at the Planck length, really, 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 really tiny. But the weird effects in our universe sometimes seem to be because of the quantized nature. Yep.
So what does each number, what does it relate to?
So, in this one, you see that there are 3 numbers there. You see we can just see there's 103, 59, 12, right? So there are 3 numbers. The first number refers to the intensity in red, the second the intensity in green, the third the intensity in blue, right, which is why they tell it red, green and blue. Okay. And those 3 combined fool your eyes into thinking it's a brown colour in that case, right?
Oh, so the initial thing is like essentially just the base work for constructing the image. Then this is like the juice.
So the juice.
In a way, I don't know how to explain it.
So what it is those 3 numbers combined. What happens is on the screen there are red, green, and blue pixels being displayed here, right? And I can just see there's red halo on that side and blue halo on this side of this pixel because they're not quite properly aligned. So we projected red, green, and blue, and that's telling you how much to fire the red pixel in the red in this pixel, and the next is how much to fire the green in that pixel, and how much to fire the blue in that pixel. But for these projectors, they don't actually have a pixel that is red, green, and blue all overlapped. So what they do is they have a red one next to a blue one next to a green one.
Oh, right. Yeah.
And so they just show them at different intensities together so that you can see it. But if you put a drop of water on your phone you can see that there are the individual different colours in the pixels. So
Oh, yeah, that makes sense.
yeah, it's just put really close together so you can't see the individuals, right? But here we have separated those out to be individual numbers so you can see them as full numbers. Now, that is only for your human eyes. I'm assuming all of you are human. Do we have anyone with quad chromaticity? Does anybody here have a yellow photoreceptor that they know of? Nope. So none of you see reddy green? That's not yellow? Okay, good. It means that you're all normal human vision. In normal human vision, well, some of you might be colourblind, so we can always discuss that later. But in normal human vision, you have a cone which detects intensity, right, which is the brightness. And you have a red, green, and blue receptor that is tuned to these different colours. So the reason this works is because we are hacking your eyes and showing you just a spike in the area that your eyes are receptive to. Which means if we had a pigeon in here, or a cat, or a dog, they might look at the screen and go, wow, that's weird, that doesn't look like an apple, that looks like a reddy green thing. Right? It's kind of like we don't have the word reddy green, we can't understand the way they see the world. Because other animals see the world completely differently to the way we do in terms of their colour perception. So a lot of these systems are designed around us, not designed around pure physics. Okay? So the way we see the world isn't perfect, and so we can develop systems which look good for us, but might not look good for other imaging systems. And these talk about colour spaces. Right? So that red, green, and blue, we have a colour space of red, green, and blue. Because we've got three numbers, we have three dimensions. Right? Two numbers will be 2 dimensions, one number, 1 dimension. A three-dimensional space is a cube, right? Have you 3 dimensions make a cube? Up the top here, when all three are maximum value, we have a white colour. White, right? We have everything as bright as it can be. That's what the sun, the light we get from the sun has all the wavelength in it, and so it appears white to us because it stimulates all three of our colour receptors to the maximum amount. We can simulate that whole colour flooding by just stimulating each one of those three equally to that strength. So we have white when it's maximum value, maximum blue down this way, maximum red over here and no other colour, maximum green over there and no other colour. What's the colour in the back corner there?
Black.
Black. Yep, because that would be 0, 0, 0, and as we saw when we said background 0, that would be the black colour in the back corner. This represents additive colours. Now most of you at primary school would have learned what colour system? What colours did you mix when you were painting with your fingers?
Blue, red, and yellow.
Blue, red, and yellow. Why are we using blue, red, and green? That's weirdness. We will be colouring that more as we go down the human vision section. But this is what we call additive colour. So when I'm shining colour onto something, then we're adding colours together, and that's red, green, and blue add together to give white. When you paint something, you're technically removing colour because white shines on it, and only one kind of colour comes off it. So when light shines on red and only red comes off it, when you take away an amount of red, you then paint it with another colour and mix those together, you're taking away more of the light. So as you keep adding colours, it goes to a darker and darker browny, muddy colour, right? Whereas if you add light, you get brighter and brighter until you get to white, right? So this is additive colours, not subtractive. Quantization, or the sampling, right? So we've had that quantization into a spec number. This is an example of sampling. So as you can see here, we have a full 256 by 256 image, and different levels of sampling that are done on a nearest value rather than an averaged value. Right? So it's just taking a pixel value and making it the same as one of the pixels inside that area. So we take that image and halve it in number of pixels, and again, and again, and again, and again, and again, until we have 2 pixels by 2 pixels. If we were to go to 1 by 1, what would it look like if it was 1 by 1?
A single color?
A single color. Can you pick from this to this what you think that color might be?
Brown?
So, well, are you thinking this one?
Not black.
So, if you look here,
Right.
this orange comes from that orange, right? Which comes from that orange, which comes from that orange, right? So you can see that pixel is the one that's being used for the when I scale up. And so it's likely that this would be this one big orange pixel, because it appears that when it grabbed these four, it used that orange one. So it's using the one kind of bit. Well, if using that one, it may pick that one if it uses that one. So it may need to be a big brown pixel, but it would be one uniform color. Yep. And it wouldn't be, in this case, it wouldn't be the average of those. It's likely to be trying to pick somewhere in the center here and pick one of these four based on, you know, random, well, not random, it will be systematic. But you can see that there's a systematic process that we're having to scale. In games, this is called mip mapping, right? Where we actually create multiple textures at different resolutions, because when there's a tree or a picture way off in the background and it's really, really tiny, you don't need to try and draw 256 by 260 pixels, you just draw a tiny, tiny little version of it. Right? So we actually use this in games as a way of creating miniature samples of things. So that's decreasing the amount of information by changing the color, the sample size, but keeping the color depth the same. The other way we can change the amount of data is by turning each one of the pixels into just a binary value. So we started out with 256 values, and this is what we call quantizing the information. Right? So when you quantize something, often what they mean is decreasing the amount of representation there is. So here we start with the 256, and even in grey you can see more of the pixels because they look a bit clearer because they're just grey level values. But as we decrease the number of grey levels, actually the second one looks pretty much like the first one. Yeah, even though it's half the amount of information, still pretty much the same. The third one, yeah, still similar. Fourth one, still similar. This one down here, starting to see here patches of colour in this one. Here, you can now clearly see there's this patch of colour, and this one is gradiated across it. Right? But then we've gone to 3 bits, so 8 different levels. So there are only 8 different possible values. And then 2 levels, and 1 level either black or white. Okay? So these are clearly bad representations. But you can often throw away a lot of information, and humans can still understand what's in the image. So as I said, we have a whole bunch of colours, 0 through 255, all those grey values. Now in this, we go back here. We go back here. That grey, those grey values are down the line from this corner to the black corner in that cube. They follow straight down the middle of that cube. Right? Because they're all equal amounts of every colour. And so we have various shades. Often the very blacks it's hard to tell apart, and the whites it's very hard to tell apart. But you can see here in processing, we can use fill 255, which would be white, background 200 is grey, stroke black, stroke some mid-grading. Right, all perfectly clear? Good. We can then also, as you were talking about, the 3 different colours. These are now examples of those 3 different colours with different values. Okay? So we can see here we're going from 0, 0 black to red and green being fully bright, which is a yellow colour. Okay? Now, as you see with subtracted colours, yellow takes out blue, so they're opponent colours. Here, you can see we've got full blue, up there is getting to full red, we've got full green, and we have these kind of yellow down to white. Right? So you can see by putting in different numbers, you get different outputs. There's a lot of work in trying to match screen colours with printing colours. We'll go into that later in the course. But the idea here is that we've got, you can change those strokes, you can change the colours of what you're drawing. That means I can control the colour of every pixel. So now we go back to drawing lines, and we have those values, and what we've done in each one is we've set the stroke to change, which then changes our colours. Right, so we're able to keep processing, and then if we have a look here, we start moving away from, okay, so everything we've been doing up to that point has been what's called direct mode, where I just said, hey, and you can see this is where I change from the previous slides, where I used the previous slides, to me recapturing it on my Windows machine now for you guys last night. Okay, so this is so I now appear to have to go back and change all of the images to make them pretty. But here, what we've done is instead of being what I was saying was immediate mode, which is I just say do this, do this, do this, do this. There's no iteration, there's no looping, there's nothing going on there. To what we call active mode, where we have a setup phase and a draw phase. So the setup phase is run once when the program first starts, and then the draw phase is called once per frame. Right? So this, if you have a frame rate of 60, this would be called 60 times per second. Right? So it starts at the top one once and then runs to the next one in cosines. Now, what we have here is a setup where it says size 400 by 400, a stroke of white, because I say set colour to white, width of 5, frame rate 10. So what do you think frame rate 10 does?
Updates the screen 10 times per second.
Pretty simple. Excellent. Yep. Updates 10 times a second. So you can change that. If you change it over 60, if you change it to like 500, your screen's probably only going to update it at 60 frames anyway, right? So you'll have some frame locking potentially. So high numbers might not get the results you want, but that depends on how the system's set up. But there, it draws the background black. I then create an X value and a Y value, half height, half width, plus 100 times cosine of an angle. I set angle at 0, and then I have angle increment by 0.05, and in this case it's radians, just because, it's computer programmers and we like radians. So this angle is actually a radian angle, so it increases that. What do you think that would do? Any ideas what that would do? I'm going to jump down and show you the code in a sec. Some of you are on your computers, you probably type that almost fast enough.
What was the question?
What do you think this code will do? Because it's got this line from width divided by 2, height divided by 2 to x and y.
It'll make a line rotate around the center.
Yep, it makes a line that goes from the center of the screen, height and width. Right, I haven't even told you what those are yet, but you work them out. That's right. And x and y, and it's using this x and y is some magnitude of a cosine of an angle and a sine of an angle. Right, so sine, if you remember math, sine and cosine. So it starts, if you have 0, you have sine at maximum, cosine at minimum, and then as the number increases, the sine goes up and then the cosine decreases and the sine gets high and the cosine is 0, and then the cosine goes negative as the sine comes down, and it basically just describes a circle. And so this is a line drawn from the center that cycles around, and the speed it moves at is frame rate by the angle of change. Right, so it's moving 0.05 of a radian every tenth of a second. Okay, so I can jump down. Actually, I'll jump down and show you that in the code. Let's go to my live coding. So let's jump into processing. I've got too many things open. There we go. Sketch folder has disconnected. Okay. So if you see that should be the same code here, and if I'll have to change the size, but if I play that, fingers crossed somewhere, right, so that's direct, and if I close that, and I change this to 60, and repress play, it will now go, fingers crossed, much faster. Okay? Now, it's pretty smooth on my screen. It's pretty jumpy on that screen. Guesses why?
The refresh rate of the projectors is lower.
I would say a combination of the refresh rate of the projector is slower, and this is going through Zoom, which means the video update is being sent over Zoom to those cameras, which are then projecting it up on stage. So yeah, this is, if I used the HDMI cable, I would probably get it smoother. Right, so it's most likely Zoom, I think, is being the culprit there. Okay, let's go back to slides. Right. This will be clear. So, all of that makes sense now? Any questions about how to set up and draw work? No? Great, okay. So we'll keep moving. We can now do very simple animation, because what we have is we have a set thing, and here we have 200, 660, and we have a background, a stroke weight, and we can do something interesting with where we draw lines or what we do. So we can animate a line. In this case, we have a line that has x of 0 to the full width, and as you might have guessed, and some of you actually guessed, height and width are predefined. Right? So they come in, and actually what happens is these two are set by this core here, size, sets height and width. Right? So those values are set in the program. And here we're going from a full width line that is increasing in y until, now you've used the mod operator, the percent operator, use that 103? Okay, some of you did, some of you didn't. For people who use this modulus operator, what do you think this modulus of height will do to the line? So each step, the line moves down. Yeah?
Is it just like multiplying it by the percent, because it's an operator that returns a remainder after division?
It's the operator that returns the remainder after division. So when I take y and divide it by height, when y is height minus 1, yeah?
Once it goes off screen, it'll come back at the top.
Yep, it just slides to the bottom of the screen, and then when height y is at the height, it gives you 0. Right, because it's divide gives you 0 remainder, and so when it's 1 below the height, it returns 1. So that's a way of animating a line that just drops off the bottom, drops off the bottom, comes back at the top. Actually, one of the things we do in computer games, when you've got like characters running in from the side or coming down from above, what we tend to do is when you shoot them, we don't delete the object, we just push it to negative space so you can't see it. Right? And so all of the enemies are just sitting in negative space outside the screen, and when we need a new enemy, you just bring that enemy back on the screen, and when you kill it, you make it move from there to off screen. Right? Because U and delete actually take a lot of time to create and destroy objects, and so what we do is we just hide them by moving them off screen. Right? And we let the graphics card go, oh well, I can't see that, so I won't draw it. Right? So that's actually one of the techniques, is to not do this to things so you can hide them off screen. Okay, so more basic shapes. Where we just use line there, we also have rectangle and ellipse and triangle. Right? Now, how many of you have seen the first assignment? How many of you have done the first assignment? Oh yeah, a couple of people, that's good. So we're now getting to the point where, like, with this information, you should be getting pretty close to being able to do that first assignment. Setting the background colour, we set a stroke colour. The stroke colour is the boundary colour, that 1 pixel around the outside. Well, it's 1 pixel if the stroke weight is 1, it's 1 pixel. Okay? So here, there, do not smooth the outlines. That means that no smooth means keep the outlines jaggy as you're going down a diagonal. Right? And that's why, and here you can see that these are relatively jaggy edges as it goes down. We call them jaggies. It's actually a technical term, it shouldn't be, but it is. But so we have a red fill, a green, somewhat darkish fill, and a blue with a bit of red and green in it just to lighten up the blue, rather than just intense 100% blue. And then we define rectangles. So that rectangle, 10, 10, 40, 40, 30, ellipse 30, 30, 70, 40, 30, and 70. Those describe the size of each of those and particularly where they are. Right? Now, there are multiple ways of defining these things. Okay? Can you pick from this? You see how big that red is and how big that green is. If you look at this rectangle, it's 40 by 30, and this ellipse is 40 by 30. So these 4 numbers, what do you think they represent? Yep.
X, Y on the screen, the X position, the Y position, the
Yep.
width, okay.
The width and the height, yes. So this is the position you start, so there, right? So that position in the top corner, and the 40 and 30 is 40 wide, 30 high, right? X, Y. So it's 40 and 30, and here, this circle is the same size as that red square. What does that mean? Well, it's an ellipse, as you can see, it's not a perfect circle. It's got the same maximum height and the same maximum width. So that's what we mean by giving it the same values. So here we are position of the top corner. Some of you will have noticed using graphics packages, when you draw a circle, you click and drag. Where does that circle get drawn? Below the corner that you're clicking and dragging. It's really annoying, right? Because I want a circle that covers the thing, but I don't know how far off up to here. Where is this point that I'm supposed to start at to get my line there? Right? So often you can hold control down, and instead of doing that expansion that way, you set the center point, and now when you drag it out, it expands from that point. So you just have to find the center of where you want to draw and expand it out, rather than the top corner and expand it down. Right? But it's because of this kind of graphics is why that was the default, is that you start in the top corner and drag it over the space. Triangles, this doesn't have a width and height. These are now tuples of x and y. So this is the x, y, x, y, x, y. So it finds each of the positions of the vertices of the triangle. So, I should have remembered that we made that large. That would have made it easier to see. But you can see here the jaggies, right? You can see these jagged lines, which is the no smoothing. And you can see that those heights are the same. Sorry, I should have remembered I'd done that. So when we look at specifying rectangle, this was the A, B, C, D. So the default is top left. So top and left, width and height, which is what you guys get. There are other modes. So you can actually choose which mode you want to draw rectangles in. And it's called rect mode. Simple. The normal is the corner version, so you have top left and then a height and width. But you can also have I think that I'll have to move my thing so you can see that. And it's because it's got the S on it. Shall I minimize that? If I minimize, will that work? No. I have to minimize it here. Bang. Corners. That's better. So, what we have here is that if you add the S, it says that these four values then become the top corner and the right bottom corner, right? And then in rect center mode, we have you draw in the center and you draw it out from that way. So you have a width defined in the center and a height defined, but the origin of the square is in the center. Again, four numbers is just what those four numbers mean has changed. And the last one here is where we do radius. So it's like the ellipse, we have the center plus how wide the radius is in each of those dimensions rather than the full width. It's just a half width. Okay, again, all of them are just four number representations, and it's how we interpret those four numbers. Why would you ever need these different ways of representing things? Any thoughts? Yep.
Mainly for convenience. You can do the math yourself, but sometimes it's a lot.
Yes, so that's exactly the point. You could do the math yourself, right? Because all of these are just easily mathematically equivalent. But it's just, what do you want to be how easy is it for you to do particular things with these different types of squares? Because if you have information coming in that is a center and radius information, why would you do the math to convert it to a top left and a bottom right by doing that math? You just want to display it immediately. So this gives you the option of representing information in different ways for your convenience, and to sometimes when we're coding, what we're doing is we are communicating with other programs. Right? So it's not about what works best in the machine, it's what works best to communicate to other people what you're trying to achieve. And so sometimes the center and a width is the right way of doing it. So for ellipses, we have exactly the same thing. So we have for the center and width and height, which is that default way of doing it. But then, as I said, you can, in some graphics packages, sometimes it's holding down Alt or Control, one of those, that when you draw a circle, you start in the center and you give a radius and a radius in X and Y. Four numbers, different representations. Right, and I think the last couple of things before we stop is the order in which you draw things is important. So those of you who have seen assignment 1 will recognize that my tree drawing in assignment 1 seems to have triangles in the front drawn over top of triangles in the back. So how you do that is by ordering the order in which you draw things from the back to the front. So when I draw the red square, and make those, I didn't make it bigger. So when I draw that red square, if I draw the red square, or red rectangle, and then the ellipse over top of it, I see red, then the green draws over top. Here, I drew the green ellipse first, and then the red rectangle second, so the rectangle was the most recent thing drawn, so it gets drawn over top of what was already there. Okay, so that allows you to do that sequence. And could be at 50 minutes, so I've got 4 minutes to go. The last thing I'll mention in this lecture, and the last thing we're talking about, is when we start adding additional interactions, we can refer, instead of just X and Y, which we set as numbers, we have some values that we can refer to, and this is the mouse X and Y position. So here we have mouse X and mouse Y, and I can then draw interactions based on the position that the mouse is at. So here you can see I've got drawing where I do corners mode, so it says that it's corners, so it's going to be in the center, so I have each corner. And when the mouse is pressed, I start drawing, and when my mouse is dragged, it updates C and D, and so I have something that is drawn initially as a point, because all four are the same. But in the draw function, it draws from AB, where I first click the mouse, to CD, where I'm dragging the mouse. So that is your standard click here, draw a rectangle. Because you click, and then as you drag, it draws the rectangle to the current mouse position. There, you've got drawing. And because its background white is destroying everything on the screen while it does that. Right? How we actually do this in a program is we create a new layer, we keep the old layer, we create a new layer, and we blank out the new layer until we've decided what it is. And once we've decided what it is, we then apply that blank layer, that new layer to the original layer. Right? So that's actually how your graphic programs work. But this gives you a simple way of drawing a rectangle. So our processing is working to do this is we have that setup phase, the draw phase, we have a wait on mouse and keyboard events and on the timer that gives us how frequently update. Right? So what happens here, it comes in, it's waiting, view mouse and keyboard events, and they can operate independently, and then it does frame update and it calls draw again. Right? And then comes back out, it's waiting for the next frame update, and then it can process those keyboard and mouse events independently. Right? So those are interrupts, they'll operate if you do is mouse is pressed, that will operate independently of the draw loop and process it. So what we have is, and this was going to be my last demo to show, is moving the mouse around I'll also say, yes, this is me using Visual Studio Code. I prefer to code in Visual Studio Code because it gives me all of the other files I'm operating with rather than just the processing file I'm on. If you want, you can download Visual Studio Code, download the processing plugin, point the plugin at your processing for executable on your Windows machine, and you can then code in Visual Studio and display in processing. Okay, so you don't have to stick with the processing editor. It also gives you dark mode, and this is just showing me moving my mouse. As I move my mouse, I draw ellipse. As I click, there's a mouse click. I draw a big rectangle, and then on mouse drag and mouse press and mouse release, I draw different interactive components. So you can see here, I'm moving my mouse. I click it at that point. I move my mouse. I click, drag, release, and move my mouse again. Right. Okay, that's 2 o'clock. We'll talk about pumpkin keys on Friday. Oh, Thursday. See you tomorrow.
I was supposed to come to the first one, but I wasn't signed up or something. I might have missed a few.
Right. Oh, the tutor's tomorrow. So you haven't missed any tutors?
Oh, no, that's not fair.
Okay.
I was just going to ask you. I know about Visual Studio. What would you recommend if I was trying to make a game or something? I know that games in Unreal.
So what I would do is, well, yeah. So that's a longer question about making a game.
I'm just interested in the course.
Yeah. So we're gonna make things. Two slides away. The difference between the animation course and computer graphics. Okay, so in our graphics courses, we will increasingly be more algorithm and coding focused, and there's a bit of math as well. Whereas the animation courses are much more design and output focused, and using more drag and drop tools rather than low-level programming and understanding the low-level graphic components. Right, so for example, our second year game engine course, I teach Godot and Unreal, and Alex will be teaching shader programming and how to actually code up the shaders that generate the images.
Okay, yeah.
Right, so whereas down the hill, they'll talk about how you use After Effects and how you use programming and use the drag and drop interfaces that kind of just process without you understanding any of it. Right, so that's kind of the difference. There are different markets for jobs as well.
Yeah.
Yeah. So I'll just end the Zoom call and I'll stop. Oh, there was some chat. So I'll stop.